Welcome to today's lecture. So, during the past 4 lectures, we were discussing about the response of aqueous inclusions to heating freezing in a microthermometric apparatus, and we know that we have studied them in chips made out of the wafer of the sample that we have considered, which have been taken from a entity like any particular rock unit in the crust or an ore body, and some such locations where we want to study the geology. We especially in particular reference to the characteristic of the fluid and the way the fluid evolved, and also the to ascertain the probable origin of the fluid which gave rise to the ore or the rock, as our interest may be. We have seen the aqueous inclusions, the aqueous biphase liquid plus vapor inclusions, and the aqueous polyphase inclusions containing daughter crystals of sodium chloride, that is halite, sometimes with more than one daughter crystal like sodium chloride and potassium chloride, which is sylvite. And in some such situations, we can understand the response to heating and freezing with help of known phase relationship in such kind of fluid mixtures. So, fluid inclusion studies in a way makes us go through or to have a good understanding on such phase relations, which are very essential, and it is also that the fluid inclusionist, in order to interpret and make the best use of his microthermometric data, will always be taking help of such kind of phase diagrams, phase relationships. And as we know that the fluid in the earth's crust giving rise to the rocks, the mineralization, ores are very complex fluids containing multiple anionic and cationic species, and are trapped at variable pressure temperature conditions, and are after the entrapment process they undergo post entrapment phase change, and we see them in various combinations of liquid plus vapor, or liquid only, or vapor only, or liquid plus vapor plus one solid crystal or more than one solid crystal. Till so far we have been able to make our understanding clear as to how to use the microthermometric data for volumetric measurement of the inclusion fluid in consideration. We freeze them and then note down the melting temperature of ice or hydrohalite, and in case of polyphase inclusion like halite or sylvite bearing inclusions, we note down the temperature of dissolution of the solid crystal, and then calculate the chemistry, bulk chemistry, in terms of the weight percent NaCl equivalent of a particular aqueous inclusion, and with the value of the weight percent NaCl equivalent and the temperature as it may be. In case of a biphase inclusion, it is the liquid vapor homogenization temperature, or in case of a polyphase inclusion, it is the dissolution of the daughter crystal. If it is higher than the temperature of homogenization, we use these and use standard formulation that have been formulated based on limited volumetric measurements made on such kind of fluid mixtures, and such kind of experimental data are available in the literature, and with some empirical fitting of the experimental data, the PV/Tx relationships can be formulated and they can be used to calculate the density. And once we know the density of the aqueous inclusion, we also use formulations which have been worked out by many workers in fluid inclusion research, to calculate the isochore, the slope of the isochore, the dp by dt slope of the isochore, so that we can construct the isochore of such inclusions in a PT space. And that is exactly the exercise that what we call as the thermobarometry. So, when we record the measurements in our experiments, they are the microthermometric data, and what we essentially were looking for is to ascertain the temperature and pressure conditions of the fluid, in turn the conditions, the pressure temperature conditions in which the minerals formed in the earth's crust. So, we have discussed the situations pertaining to the liquid rich inclusions, and also we know that there could be inclusions which could be trapped as vapor from the vapor stable field, and they are manifested as liquid plus vapor with a very large or a very high proportion of the vapor, and they are the vapor rich inclusions which homogenize into the vapor phase. In case of the aqueous liquid inclusions, we also in case of the aqueous liquid inclusions, when we discussed that once we have an isochore, if we have an independent estimate of pressure, we can get the temperature for the formation which you know as the temperature of trapping, and which sometimes can be done in situations where there are some independent barometry. Same is also could be true if there is some independent geothermometer, in which we can also do this reverse process, that if knowing the temperature we can also if this is the isochore, then if we know that the temperature of formation of a particular mineral is somewhere here, then we can also know the pressure by, so this will be the pressure of trapping. So, this is essentially the exercise which we call as thermobarometry in fluid inclusions. Now, on this diagram we will try to see that whether such kind of thermobarometry exercise can be done in such a way that we will not be needing any pressure correction. Previously we discussed that if on the isochore, if we have a pressure known at any point, we drop a perpendicular to the temperature axis and get the temperature of trapping, and the difference between the temperature of trapping and the temperature of homogenization is something which gives us an idea about how much of correction would be required to our temperature of homogenization to know the true temperature of trapping. Now, there could be some situation where we will not be needing any pressure correction, and that is a situation which is depicted on this diagram. So, it will be a thermobarometric exercise with aqueous inclusions. It will be actually an aqueous biphase inclusion. So, here the pressure will be equal to the vapor pressure. Now, what the condition could necessarily be? As we know that the condition is necessarily that this is the boiling curve where there is coexistence of liquid and vapor. This is the critical point here, somehow this dot is below that. So, here we imagine a situation where the fluid in the subsurface anywhere in the earth's crust where the fluid is being channelized, because of some physical process where there is sudden movement of the fluid, a packet of fluid to a lower to a much shallower condition, the temperature is high, then the fluid will essentially go a process, there will be a coexistence of liquid and vapor, and we will call this condition as a boiling situation, which we will discuss a little later about its significance. But this essentially indicates that the mineral growth process, the entrapment of the fluid inclusion, was taking from a fluid which was in its heterogeneous condition. But again we stick to our assumption that the entrapment is homogeneous, means on this particular point when there is a host crystal which is crystallizing, which is precipitating, will entrap either the liquid, either a packet of liquid or a packet of vapor, not a mixture of the two. So, in that case, as we discussed before, if a vapor is entrapped inside in the solid crystal lattice, then with decreasing temperature and pressure condition, it will give rise to inclusion which will have a large proportion of the vapor is shown in the inclusion which is below here, and the liquid which will be trapped here will also be evolving on the liquid vapor curve, and then finally it will be at room temperature we see them as a liquid rich inclusion with a smaller proportion of the vapor. The situation is that when we heat these two and then the necessary necessary condition for such kind of a situation is that if this is the host crystal, then these two inclusions, one which will be a very vapor rich inclusion like this, or one which will be a liquid rich inclusion like this, these two inclusions like shown here by these two sketches, they have to be coeval. Coeval means they should have been trapped at the same time at the same conditions within the single crystal of the host mineral. This represents one single grain of the host crystal. Within the single grain need not necessarily have to be on the same plane, but have to be a part of the random 3-dimensional network, not trail bound. In this case, these two inclusions which are coeval, one is a liquid rich inclusion with a small vapor bubble, and the other one is a vapor rich inclusion with a very negligible proportion of liquid. If they are heated, then both are going to homogenize. So, in this case, when both will homogenize, so this homogenization, the first inclusion here, the one which is shown as the one liquid rich inclusion with a small vapor bubble, will homogenize as before, as we have discussed the homogenization behavior of a liquid plus vapor inclusion which homogenizes L plus V to L. So, this will homogenize into the liquid phase. The inclusion which is shown here will also evolve with heating along the boiling curve, where the liquid phase will go on diminishing in its amount, and the homogenization at the homogenization state, it will be the cavity will be completely filled by vapor. We also discussed about the practicality of noting down the temperature for homogenization, where the homogenization is L plus V to V, where there may be a little bit of an uncertainty. So, here the condition is that the homogenization temperature, that is this L plus V to L and L plus V to V, both these homogenization temperature which is the TH have to be same. So, that means this the homogenization which is giving rise to L plus V to L and the L plus V to V have to be nearly at the same temperature. So, the necessary condition is that these two inclusions have to be coeval primary. They may be also made in cases where their secondary word belonging to the same generation can also be utilized. They have to be coeval, and the temperature of homogenization of these two inclusions, one to the liquid state and the other to the vapor state, has to take place at the same temperature, at least within the acceptable uncertain limit of plus minus 1 degrees Celsius. Okay. So, that's a situation in which then we would not be requiring any pressure correction. So, that means here the homogenization temperature of these two inclusions which takes place at the same temperature does not need any pressure correction, and the pressure on this boiling curve will be the vapor pressure of the water of the specified weight percent NaCl equivalent, because we would have measured the salinity of the liquid in this case both by the depression of the freezing point of the ice, depression of the freezing point that we discussed before, and the salinity is known, and then that particular salinity, the vapor pressure of water can be calculated. As we know, the maximum vapor pressure can go in case of a liquid vapor coexistence to 220 bars, that is the critical point, and anything below that. So, if suppose this particular point corresponds to about 100 bars of pressure, and if we establish that this particular pressure is a hydrostatic pressure, then we can calculate that what is the depth at which this process took place, or where the mineral formed. In case of the aqueous polyphase inclusion with halite daughter crystal, it is also possible to do thermobarometry, but here the only situation is that if we look at this diagram, on this diagram as we discussed before, this corresponds, if a situation in which this is always will be corresponding to situation where the Ts NaCl, that is the temperature of dissolution of the halite, should be greater than the temperature of liquid vapor homogenization. As we discussed before, that here it's already mentioned here, that the Th, in this case the temperature of dissolution of the daughter crystal Ts NaCl should be greater than the THLV, the liquid vapor homogenization, and under that situation this particular method of estimating pressure from the halite dissolution is applicable. So, here on the diagram what we see that an inclusion which initially had liquid plus vapor plus one daughter crystal of halite, that is sodium chloride, it underwent liquid vapor homogenization and the homogenization to liquid at a point corresponding to, let us say, T1, and that is equal to the Th. And after the disappearance of the vapor phase, the system evolves in a liquid plus halite field. So, during the evolution of the liquid plus halite field, the halite crystal keeps on dissolving in more and more amount, and its volume reduces, and it reaches a point where the liquid, the halite completely dissolves, where it is written as P6, and that is the Pm is corresponding to the pressure at the melting of the halite or dissolution of the halite, and it moves through in this liquid vapor curve and reaches to a point here. So, as before, we could also approximate the entrapment condition, entrapment pressure and temperature condition from the dissolution temperature of halite as a minimum approximation, because from here onwards the inclusion again will follow a constant density isochore as shown here. For example, temperature corresponding to T7 and T8, and we will not have much of a constraint here to exactly know at what point the inclusion actually formed in absence of any other independent consideration like a barometer or a thermometer, which we discussed before. But then this particular situation, it was initially a crude method was devised in which the sodium chloride's properties of its thermal expansion, the coefficient of thermal expansion, the amount of sodium chloride that dissolved from T1 to Tm, T6, let us say this is T6, the T6 corresponds to temperature at which the halite dissolves. So, corresponding to T6, change in the volume of the host crystal, and then the total amount of weight percent NaCl equivalent that could be calculated on the basis of the dissolution of this halite crystal. Some crude method were devised from which some standard tables of volumetric measurements, experimental data, a value of the vapor pressure, because this pressure also will be the vapor pressure at the dissolution of halite corresponding to temperature of T6. There has been some recent work as referenced here. There has been a formulation on the pressure at the dissolution of halite, melting of halite as Pm is given as this expression, in which this alpha coefficients alpha 0 to alpha 4 have been empirical feed parameters, and these have been fitted as second or third degree polynomials in Th, where the necessary condition is that the temperature of homogenization has to be L plus V to L, because this corresponds to a situation where there will be liquid plus halide stability field. It is not worked out on the vapor plus halide stability field, and such kind of formulation also has an uncertainty of about 1.424 megapascal, means that translates to about 14 bars of pressure. And these authors also have given a revised method like the one we discussed before, that the salinity of an aqueous inclusion with homogenizing by a method by disappearance of halite, where the salinity could be calculated from the temperature of disappearance of halite or melting of the halite as a second degree polynomial in temperature, with the with a equation almost like A0 plus A1 Td or Ts plus A2 Ts square, so on. So, this one this equation was also devised as an improvement, where weight percent NaCl could be represented as a beta 0 plus Tm plus beta 1 beta 0, because I is equal to 0 here, beta 0. So, this equation will be something like of the type of, so weight is equal to something like beta 0 plus beta 1 Tm, and this beta 0 and beta 1, these coefficients are also fitted as empirical fits to temperature of homogenization. So, that brings us to we conclude that what are the possible microthermometric parameter or microthermometric data that could be acquired on the aqueous inclusions. In case of, we will review it, but before that, so the coming to the concluding part of it, that how we could use it, or how could we represent the data, microthermometric data. So, the standard practice of presenting the microthermometric data is by the method of histogram, and on a histogram we know that we choose something like a class interval and then calculate the frequency in terms of, here as shown here, the number of inclusions, and suppose this kind of histogram is prepared for all the data that we generate, salinity, temperature of homogenization, and also the density that we calculate for the inclusions. So, we keep it in our mind that when we coming to a stage where we are to present our data, means we have acquired the data that we intended to do in a particular considering the problem that we picked up, the samples, the number of samples that we decided to work on, and per sample the number of inclusions that also we wanted to work on. We have finished the data acquisition and now we present them. So, this presenting the data only with an intention to look at the kind of pattern of distribution that we see in the data. For example, it is shown here that if we, and since it is statistics, so we have to go by the basic rule of as to how the class interval has to be chosen. This class interval for the guiding factor for the class interval is essentially the minimum value and the maximum value. Let us say, for example, we in the course of our acquisition of data, we find that the salinity is starting from very close to values of 0, let us say even 0.1, 0.2 or 0.5, and can go up to 40, 50, 60, even 70% NaCl in many specific cases. And then we think of choosing a class interval and then calculate or the values, the number of inclusions falling in that particular class interval, and we plot a histogram. See, the histogram is plotted with only the intention to see whether we get a single unimodal distribution of the salinity, or we get as is shown here. Just for example, if we see here, then this kind of a distribution we call it a bimodal, means there are two distinctly different salinity values, a moderately low or to low to moderate kind of a salinity value. Suppose, for example, if I have divided this range into as 4 weight percent interval, then it will be 0 to 4, 8, 12, 16, 20, 24, 28, 32, 36, 40 and so on. So, we see that there could be this kind of a distribution is basically interpreted as a bimodal distribution. It gives us some idea that, well, then there must have been some because essentially we also have to keep it in our mind that when we see the inclusions and we are essentially trying to understand the primary phenomena of the formation of the particular ore or rock, then essentially when we are looking at fluid inclusions in them, we know that they are a result or a manifestation of deposition. Means the spectrum, the fluid characteristics during which that particular mineral crystallized, the fluid changed in its characteristic in this way. So, that could later on could be assigned as to what this change could be interpreted as, whether there are two different types of fluid or the same fluid possibly would have evolved in such a way that at one particular condition it was very highly brine, highly concentrated brine, and then it evolved down to and again attained another value, and or to be more specific, the depositional process was more extensive in corresponding to salinity values that is shown here, with continuous deposition of that particular mineral which are showing. And if we take it for granted that there has been no bias in our sampling of the fluid inclusions, and we have chosen the right fluid inclusions, that is also itself is a practicality of fluid inclusion study, to choose the right inclusion, not to have been leaked earlier and away from healed cracks for the primary inclusions. So, the chances of the content of the inclusion being later disturbed by later activity, such kind of situations are minimized, and we are able to plot them in a histogram. So, whether it is a temperature or salinity or density, we can plot them as histograms as shown here. So, here on the diagram below we see that these histograms are plotted in such a way that they are on the either side of the axis of this when we are dividing them. So, with two different types of legends shown. Sometimes when we have in the aqueous biphase inclusions which are both liquid rich and vapor rich, and also we get situations where the vapor rich inclusions homogenize into vapor state, then their data can be interpreted or presented in this way, so that it gives us an idea that well, there are aqueous inclusions which homogenized into both modes, and if in an very ideal condition where we could see that the frequency or the mode for occurrence of a liquid phase homogenization is also coinciding with the vapor phase homogenization, and we also keep it in mind that we have taken the coeval liquid and vapor inclusions, then we go on to interpret important physical process, say for example, a boiling in this case. So, we will see some of the case studies where in many of the different types of situations where such kind of histograms are as a routine procedure for presentation of microthermometric data to understand the fluid characteristics. And then again we have paired data on temperature of homogenization and salinity. In some situations people also do plot as the Tm, that means the depression in freezing point on this axis also, but it is always a good practice to it is a choice. Generally we prefer to draw this diagram on temperature of homogenization and salinity. Before interpreting this diagram, we also know that these temperatures are the temperature of homogenization, which are not corrected for pressure because we did not have any other independent parameter available with us. So, these diagrams are very popularly known as a fluid evolution diagram, this temperature and salinity diagram, because here we understand that what little bit of deficiency what we have because of non availability of pressure correction will be somehow compensated by the statistics of measuring hundreds of such inclusions in a particular sample, particular environment, and in which we are more interested to have a look on the what is the range in values of the temperature and the salinity in which the deposition process occurred. So, on this diagram, this top part is a critical curve, which we know that this corresponds to about 374 degrees Celsius for a pure water, and we can calculate the critical temperature at varying concentrations of NaCl, and this critical curve is plotted here. And this one is the halide saturation curve, means this corresponds to 26.38% at room temperature, and as the temperature goes on increasing on this axis, and with the solubility of NaCl goes on increasing, and that is how this curve is labeled as the halide saturation curve. Ideally, when we talk of aqueous biphase inclusions, they are likely to be falling in these regions. Aqueous polyphase inclusions with halide daughter crystal are likely to fall on this halide saturation curve, but at times we also do get aqueous biphase inclusions whose points fall beyond the halide saturation curve without actually having halide daughter crystal in them, and which happens because the chemistry has been such that the halide daughter crystal could not precipitate as independently as a halide daughter crystal, but because of the presence of other soluble salts, other chlorides, the solution is actually very briny. It would this weight percent NaCl equivalent could be more than what could be corresponding to the saturation value. So, now more important here is what we say is the evolution, the fluid evolution path that we think of. The fluids in the earth's crust can evolve in some specific ways, that either the fluid could cool, or the fluid could boil, or the fluids could mix. So, fluid mixing is a very common phenomena in crustal processes, and there are many ways the fluid mixing is manifested. So, this is an idealized diagram considering the white circle which is to be the original aqueous fluid. What will happen if the fluid, and suppose this particular fluid has got a temperature and salinity value, and this salinity value will have kind of an inverse trend, decreasing value for both temperature and pressure, temperature and salinity. And if we, with this kind of temperature also helps us in understanding the fluid ancestry. For example, a particular fluid is having a very low salinity and low temperature, it is likely to be the meteoric water, which is where it is almost the freshly precipitated water, rain water, which is just percolated through the fractures in the fracture network in the rock, and is just not that, is low in its salinity and also not that very high in its temperature. And as against that, the fluid could be very high temperature and salinity, which we will be discussing later on, and this kind of a trend would tell that possibly there was some fluid mixing process. Even we can have the lines which are shown by arrows towards 5 or to 1. This also could be trends possible in fluid mixing, mixing of low saline and high saline fluid, which also happens. It could be a fluid which is very high temperature but low saline, as it happens in a metamorphogenic fluid. Now, the most interesting part or most interesting path of evolution of a hydrothermal fluid is by boiling. Means from an originally homogeneous liquid, vapor phase gets separated as when the pressure decreases with very little fall in temperature in an adiabatic condition. In that kind of a situation, the vapor phase gets separated out of the liquids. So, as and when the vapor phase gets separated out of the liquid, because of the very low concentration of the salts in the vapor phase, the residual liquid becomes more and more rich with NaCl. So, that gives a trend of increasing salinity with very negligible change or very little change in the temperature of the fluid. We get a very high salinity trend, and that's a boiling case. But as before we said that boiling can be inferred with accompanying evidence of coexistence of coeval pure aqueous biphase inclusions with liquid rich and vapor rich, and that those two inclusions would be homogenizing at the same temperature. So, here some of the review points: that aqueous inclusions are the dominant type in most environments where fluid plays a role. Although electrolytes other than NaCl are present in variable concentration, salinity is always expressed as NaCl weight percent equivalent. That is not a serious deficiency, but it definitely introduces some amount of error in calculating, in knowing the exact salinity value. And the temperature of fast melting, that gives us an idea as to whether salts, whether it is a pure sodium chloride or salts other than cations other than sodium are present. And the temperature of melting of ice is used to calculate the weight percent NaCl equivalent, that is salinity of the fluid, total dissolved solid, and the temperature of dissolution of solid crystal, that is Ts NaCl, is used to calculate the salinity, and also the density is calculated from temperature and salinity. So, it is possible to have both temperature and pressure values from homogenization of aqueous biphase inclusions if trapping was from a fluid that was boiling. It is possible to do barometry with the halide bearing daughter crystals, halide bearing fluid, halide daughter crystal bearing fluid inclusions, where the Ts NaCl necessarily has to be above Th, because if Ts NaCl happens to be below Th, then what we are getting at the homogenization is actually the liquid, it is on the boiling curve, and we know that it will follow an isochore where the temperature and pressure cannot be further constrained. So, isocores are useful and help in determining trapping temperature if pressure of formation of the host mineral is known, or trapping pressure if temperature is known, as we have discussed. Pressure corrections of homogenization temperature is more significant in case of fluid which have a very low salinity, but there generally pressure corrections are low in case of high salinity and high density. And the paired salinity TH plots not only give the important clues on the origin of the fluid, but also indicate the way the fluid evolved, like a fluid mixing, fluid boiling, or even simple cooling sometimes also is an efficient process in bringing about deposition of many minerals. And the study of fluid inclusions actually leads us to understand the intricacies of the phase relationship in the complex brines, water with variable amounts of different types of electrolytes. So, that brings us to the end of the discussion on the aqueous inclusions, and we will see them later again in different while discussing some different case studies. So, that we will continue discussing on the other types of inclusions in the subsequent classes. Thank you.